Alright, finally, the final video for today. So, I want to talk to you about my product rule, which is, I sometimes call the Uber product rule because it is all-encompassing. Well, encompasses a lot anyway. So, here's the deal. If we have W1, W2, W3, V, finite dimensional real normed linear spaces, alright, thinking of U as being a subset of V, and suppose you got a beta as a basis for V with coordinates x1 through xn. So these will be the ones I take partial derivatives with respect to here. Let gamma 1 be W1 through W sub m1. That's a basis for W1. And W gamma 2 with V1 through Vm2 be a basis for W2. Gamma 3, epsilon 1 through epsilon m sub 3, a basis for W3. Alright, that's a lot, isn't it? I'm going to assume that there's a product, star, that goes from W1 cross W2 to W3. For those of you who are students of abstract algebra, this is not a binary operation necessarily, because I'm not saying that W1, W2, and W3 are the same space. I mean, these can be totally different normed linear spaces. And yet, there's some way, right, of combining things from W1 and W2 to get things in W3. And not only that, it's got this linearity. So I can pull constants out of either the first or the second slot, and I got this additivity, right? So what I'm looking at then is functions that go from this open subset of V into W1 and from the subset of V into W2. So I can define their star product, if you will, point-wise in terms of this given product, star product. So f star g of a is f of a star g of a. All right. Furthermore, this is so far everything up to this point has just been a setup. All right, and I assumed for purposes of convenience that f and g are both continuously differentiable. I'm sure you could weaken that to get some theorem for functions which are merely differentiable given particular conditions, blah blah blah. But let's just be greedy and assume that f and g are continuously differentiable at a. That means I can build derivatives from partial derivatives, which is kind of nice. All right, moreover, denoting the partial derivative with respect to xj by a partial j, I have that the jth partial derivative of the product of f and g is this. So this is like a generalized product rule, as I was saying. And so, of course, from that you can build, likewise, the formula for the differential. The differential of f star g is the differential of f star g of a times plus f times the differential of g at h. This is the product rule. Let me show you how to prove it. So the reason I did this, well, let me skip the reason. Let's just go to the proof. I'll talk about reasons when I got reasons in front of us. So we can define structure constants Cij k in R such that Vi star Wj is some Cij k epsilon k. The fact that we've assumed star is linear in both slots means that I can write its action in terms of these structure constants, in fact. But these such constants have to exist by definition of the product. And but vice versa, if I gave you such constants and I assumed that you extended this bilinearly, that would uniquely define such a star product. But that doesn't have much to do with what we're doing here. I'm just saying. All right. Anyway, the structure constants are really just bystanders. They just keep track of where things go and allow us to do regular calculus. But so I won't say much more about them here. So suppose you got the functions f and g continuously differentiable with component functions f1 through fm because w1 is m1 dimensional, and g1 through gm2 because w2 is rather m2 dimensional, and these are both continuous at a. Then we can calculate the star product of f and g and figure out what the component functions are of this. Is R, I don't know, whatever, I'll leave that to another department. What am I saying? It's party day, there's no time for grammar. Okay, so, here we go. So this times that, so we got the sum, I equals 1 to m1, j equals 1 to m2, fi, gj, and then the product of the basis But remember, I can rewrite that in terms of the structure constants and the basis of W3. Then what I do is by properties of finite sums, I can pull that one out front, and I can keep these two in here. If you've never proved that sort of thing, I can tell you how to do it, but it's not that exciting, so I'm not going to say more about that here. And so Fij, Cij, pull the basis out. At this point, it becomes clear that this monstrosity right up in here is the kth component function of f star g. Furthermore, it should be relatively clear that f star g is continuously differentiable because it's built from the product and sum and constant multiple of continuously differentiable functions. But let's not jump the gun just yet. If we calculate the partial derivatives of this, it will become manifestly clear that these are in fact continuous functions, given the continuous differentiability of f and g. Let's look at that. So here it is. Partial derivative of f star g is the partial derivative of this. How do you differentiate? Component function by component function by component function. So I pull the constant out because it's constant, and then we're left with the derivative in the nth direction of Fij, plain old ordinary garden variety product rule, a bunch of times, gives me that. And then I just rewrite sum, this piece and that piece separately, and then just undo the steps that got us to these formulas in terms of structure constants to rewrite this in fact as the partial derivative of that star g plus f times the partial derivative of that. Now, okay, so we're assuming that this is continuous and that is continuous. Oh, I guess technically I also need to know that the product of like the star product of a continuous function. I mean, I know that f and g are continuous at a because they're differentiable. So differentiability of f and differentiability of g implies continuity of f and g at the point. But it is true. Maybe there's a small gap here. I need to prove that the star product of continuous functions is continuous. I'll leave that to you guys. I think it's true. I'm pretty sure it's true. It's definitely true for my examples. But anyway, so like I said, the last step I used the calculation of the previous, this one. I use this calculation to make this track back, all right? And there it is. With the gap I just said, again, this is continuous. Excuse me. So that means that the f star g is continuously differentiable, and this is the formula for its partial derivative, which then, from that, the theorem follows, right? Theorem being that the partial derivative of this is that. We just calculated it. Hooray! And then once you have this, you can use the usual connection between partial derivatives and differentials to build that formula. Maybe I do that on the next page. I don't know. Let me see here. Oh yeah, there it is. Finally, we can construct the differential. So here's the gory details. df star g of h. Now here h is the sum over L of h sub L, r sub L. Use linearity. Well, I just use I forgot the number of the theorem, but if the differential exists, then you can build it from partial derivatives theorem. We talked about it today, I've forgotten its number, but, and then this was shown to be that, and then I just rewrite this, collect this and factor that out, and collect this. I'm using linearity of the star product in both entries to do that. Technically an induction, if I have linearity for two things, I got linearity for n things. I haven't proved that either, you got me. So anyway, there it is. That's the differential of f at h, that's the differential of g at h, and there you go. That's the product rule for the differential of the star product. Now, you're like, what's a star product? Well, I think the real question to ask is, what's not a star product? So, for example, if I set W1, W2, W3, R, and V equals to R, then this thing we just did is the usual product rule from Calculus 1. Of course, that's not surprising, since that was the critical step I assumed in the middle to prove it. 2, if we have W1, W2, W3, R, and V is Rn, then we get the usual product rule for, maybe this is really the thing I did in the middle. I find you got me. I'm sorry, I don't think there's really much daylight between this and that. but, you know, whatever. All right, so if we choose all the w's to be real and the domain to be Rn, that gives us the product rule for partial derivatives of functions. If I pick w1 to be R and w3 to be w2 equal to w3, what? I'm not sure what I want here. Oh, I guess the point is that this could be any normed linear space. Why is VRN? Oh, okay, fine. I'm sorry. It's right. I just have to come to terms with my own notes. So if I'm looking at a vector valued function multiplied by a real valued function, partial differentiating with respect to a coordinate, you know, Cartesian variable, well, then I get partial f partial xi f times v plus f times partial v partial. So this would be the product rule for like a scalar function times a vector valued function. Yeah. If I have w1 and w2 both Rn, w3r, then I'm suggesting that v dot w gives a star product. In other words, just to be pedantic here, I'm saying v star w is equal to v dot w. That certainly has the needed linearity, right? Its output is a real number, and so that's what the star product looks like for the dot product. The derivative of the dot product is the product rule here, dv dt dot w plus v dot dwt. If you took my calculus 3, I certainly proved that and used it to study the Frenet frame geometry. Likewise, if we take w1 and w2 to be R3 and w3 to be R3, and we're thinking of v star w equal to v cross w, being the cross product in 3 dimensions, then we get that lovely product rule. And of course, we can also let w1, w2, w3 all be n by n matrices, and take a domain of real numbers just to keep it, you know, concrete. In other words, we can look at a path of matrices, 2 paths of matrices. The product of 2 paths of matrices gives yet another path of matrices whose velocity is related to the velocities of the original 2 matrices according to this natural product rule, which respects the non-commutativity of matrix multiplication. There you go. Yet another product rule that we actually use in differential equations. Of course, there's also the case that all the w's are complex numbers and a domain is complex numbers. Then we can talk about, I'm using x and y as the Cartesian real variables inside C. Then we have these partial derivative, you know, we use these product rules for complex valued functions of a real variable x and real variable y. So, yeah, I mean, I guess that was a lot of notes. Oh man, I'm out of notes. So there you go. That's the product rule, and I think that's all I should tell you for today. Next time we'll pick up. First of all, any questions you got about the things I said today? I know I said a lot, but basically all I said today is that, you know what, the Frechet differential, it works like ordinary differentiation. We got linearity, we got composite rule, which is you might call the chain rule, and there's also a very general notion of product rule. Provided that the product has that the product itself has to have that linearity built into it, right? But if you're talking about a product that's in some sense a linear product, in the sense that I made clear in the theorem, then we get a corresponding product rule. And so next up, I will say a little bit about higher differentiation, and I'll try to spend a little bit of time telling you guys just a little bit about what I've learned about differentiating with respect to an algebra variable. And then, if we have time, I'll start into the next chapter, chapter 3, on inverse and implicit function theorems, which, you know, it's more the same. But anyway, do ask me questions if you got them about the homework. I appreciate you being part of this class, and I hope you had a good day. Later.